still talk about the radiation pressure. Yeah, so it is like this is the intensity of the light times the area, and this is the speed of light, and this is the force. Actually, you can feel like if this is a spotlight shooting on you, then you will feel like there is some light shoot on me. Even you close your eye, you can really feel some pressure on your skin. So actually, this is the radiation pressure. As much as the light is strong enough, you can really feel it without any help of the measurement equipment. Yeah, so this is actually the force. I don't really know how to derive it or how, but yeah, there are two cases here. The first one is that if the radiation is totally absorbed by the surface, then the force like that. This is totally absorbed. And the other case is if the radiation is totally refracted back along its original path, the force is two times larger. So you can know that when you see some color on an object, it is like suppose this is an object, and then there is some light shooting on the object, and then when we see it, it means that the light are reflect and then goes to your eye. And then when you see different color, it means that suppose we have a white light shooting on this object, and then if this object is blue color, then which means that only the blue color is not absorbed by the object, and then all the other color are absorbed by it, so that you can only see the blue light after the light are shining on it, and then you feel like the object is in blue color. So if the object is in black color, then suppose all or most of the radiation is absorbed by the object. And if it is very bright, or even if it is a mirror, then probably all the radiation will be reflected, which means that here, if it is an object, then there is some light shooting on it. And if it is all the way absorbed, then this force will be IA over C. I don't know why it is IA over C. I can only tell you that why there is a 2 here. If the case is like, suppose this is another object, but the light will be reflected. So there will be some light going in this way, and it is reflected. So when you consider something like the conservation of momentum, something like that, then there is a, which is like all the energy are absorbed by this one. So the force is 1 times of this factor. And now, if all the radiation are totally refracted, which means that it is like this wave, and this it is the incident wave, and then this is the refracted wave, which means that as much as you need something like the conservation of momentum, you need to have something like F equals 2 times IA over C, something like that, 2 times to this one, to make this one from the left going left side to going right side. And yeah, it will satisfy some sort of conservation of momentum. Yeah, so there will be a factor of 2 because it needs to reverse the direction of the incident radiation. So here we also have a radiation pressure, which means that this is this pressure is F divided by the cross-section area. Yeah, I don't really know, but what it means. So it just divide many different variables. Yeah, but it is actually some sort of a particle characteristic. And if you have, yeah, probably in high school physics class, yeah, your teacher may probably have tell you that the light has the duality, which means the light sometimes has the wave property, and also sometimes it will have a particle characteristic. And actually, this like pressure, momentum, or force is related to the particle characteristic. For the wave, we don't really consider the momentum, something like that, or the pressure. Yeah, so next one is about the polarization. Just now we have already watched a part of the video about this polarization. So here, the electromagnetic waves are polarized if their E field vector are all in single plane, called the plane of oscillation. So yeah, so it defines what is polarized EM wave. And of course, we have polarized EM wave. Also, we have unpolarized EM wave. So, of course, for generally, we can see the EM wave if it is propagating through the x-axis, So it is like the E field oscillate in y-axis, B field oscillate in z-axis to this direction. And then if you see it from the x-axis to this side, if the light is unpolarized, the E field can be pointing to either direction, or in such a way, this is a quick way to symbolize the unpolar light by this one. So if you like, it has a horizontal component. It also has a vertical component. So we can also use this one to represent a polarized light. If it is polarized, it tells you that all the E field vectors are all in the same plane, which means that for this one, the plane is this plane. Actually, the plane perpendicular to the paper. So this is the plane for oscillation, and it tells you that if the electric field vector are all in the same, all in a single plane. But for this case, it is unpolarized, so we have many different planes go through this central axis. So they are not all in the same plane. And this is all in the same plane, and we call it this one the polarized light, or more specifically, this is the vertical polarized. If it is like that, it is a horizontally polarized. So just a name. And the next one is, so suppose this is the polarization sheet, or you can say it as a polarization filter. So this line means that the polarization direction will be vertical. If you draw it like this, or more simply, you can just draw it like this. If you represent, you represent or here we will represent that the light coming from that side, which is unpolarized. So we have unpolarized light with a vertical and horizontal component. And then after it going through this polarizing filter, then only vertical polarized light remain. And in that case, the intensity Suppose I is the intensity for the unpolarized light, and after going through this one, the intensity become half of the I0. I0 is the original intensity. After going through this one, it become polarized light, and only half of the intensity remain, because another half of the intensity belongs to the horizontal polarized component. So we only have a half of the intensity remain. And for the next case, if the original light is initially polarized, and the transmitted intensity depends on the angle theta between the polarization direction of the original light and the polarization direction of the sheet is like that. So here, for that case, we assume the original light is already polarized. For example, in this direction, not actually on x or y axis, but with an angle between them. And now we have a polarized filter, which is vertically directed, which means that the polarized angle between the light, the polarized light, and also the filter has an angle of theta. And after this polarized light going through this filter, the intensity also reduced, but by a factor of cosine square theta, but not cosine theta. If you just consider it like the E field, we have a x component, y component. So this should be cosine, this should be sine, and then you don't get this square. Actually, it has a square. Yeah. So this is the expression how to calculate the intensity of the polarized light. So here we have a sample problem. So here the figure shows a system of 3 polarizing filter in the path of initially unpolarized light. So the light come from that point to here. So originally it is unpolarized with the intensity I0. And then the polarized direction of the first sheet is parallel to the y-axis. So this is vertically, because this is x-axis, this is y-axis. So for the first one, it is vertical polarized. And then the second one is at 60 angle counterclockwise from the y-axis, which means that it is polarized in this angle, and then with a 60 degree with the y-axis. And then for the third one is parallel to the x-axis. So this is like horizontal polarized. So what fraction of the initial intensity I0 of the light emerges from the free sheet system, and in which direction is that imagine the light polarized? Yeah. So here, So here before sheet 1, so it is unpolarized, and the intensity is I0. It's I0, which is here, and then I1 is the intensity after going through sheet 1. So after sheet 1, so it will be polarized. And the intensity is 1/2 I0, because it should satisfy this equation. So we have a I0 here, and the polarization direction should be vertically, because this one is vertically polarized. So after the second one, it is of course polarized. And you consider that this is vertical polarized, and then the angle between the second one and also the original line is 60 degrees. So the intensity, this is I1, and here it is I2. So I2 should be I1 times cosine square of 60 degrees. Just satisfy this 33.38 equation. Okay, so it is nothing but 1/2 I0, and then cosine 60 degrees is 1/2. So it is 1/2 square, which is I0 over 8. And then after sheet 3, which is the final case, of course, it is still polarized. And then I3 should be, yeah, you can see here, the line is polarized in this direction, which is 60 degrees to the y-axis, which means that this direction and this direction will have a 30-degree angle between them, which means that I3 should be I2 times cosine square of 30 degrees. So we can just plug in the number. I2 is I0 over 8, and then times cosine 30 degrees is square root of 3 over 2, and then quantity squared. So this whole term is 0.094I0. And then finally, this one is polarized in x-axis. So it's similar to if we just remove the second one. If we just remove the second one, there should be no light can go through this one and this one. But with the second one, it turns out that there will be more than 9% of the light can go through this 3 polarization sheet system. So this is a strange phenomenon. Yeah. Okay, so yeah, here we talk about some simple thing. I suppose you should have learned it in high school. Yeah, so here we talk about the reflection and also refraction. So refraction is like you look at the mirror, then there will be reflection. Yeah, but for refraction, there should be 2 materials. And actually, for these 2 materials, the speed of light will be different. Previously I told you that for vacuum or air, the speed of light will be a constant. However, for different material, the speed of light may change. So here, for figure A, a photograph showing an incident beam of light reflected and refracted by horizontal water surface. So you can see this is a tank with some water, and this is the light. This is the beam of light. So this is the incident wave. This is the incident wave, and this part is the reflected wave. And for this part, it is a refracted wave. Refracted wave. So it tells you that a ray representation of A. So this is the ray representation. The angle of incident, which is θ1. So this is the surface. For the upper part, this is air. For the lower part, this is water. So this is the surface between the air and water. And we can draw the normal line, which is the line perpendicular to the surface. And we can draw the incident line here. This part means the wavefront, means the wavefront of the EM wave. And this is the angle between the normal line and the incident ray. It is denoted as θ1. And it tells you that for the reflection angle, θ1 prime, which is the angle between the normal line and the reflected wave, is θ1 pi. And you know, θ1 is equal to θ1 pi. So this is the simple case for the reflection. And for the refraction, it is a bit more complicated, but here it says, when a light wave encounter a boundary between two transparent media, a reflected wave and a refracted wave generally appears shown in the figure above. So the law of refraction is a reflected wave lies in the plane of the incident and has an angle of refraction equal to the angle of incident, both relative to the normal. So which means the law of reflection is nothing but θ1 equals θ1 prime. And for the refraction, it is a bit more complicated. So here we still have θ1 for the incident angle, the angle of incidence, and θ2 is the angle of refraction. So they are not equal anymore, and the relationship between θ1 and θ2 is this one. We call it the Snells Law. Snells Law. So a refracted wave lies in the plane of incident and has angle of refraction θ2 that is related to the angle of incident θ1 by this one. So N1, N2 are dimensionless constant, and it's called the index of refraction. Index of refraction. The index of refraction is like, for example, in air, the air index of refraction should be 1, and it should be defined as the speed of light divided by the V air. Speed of light means the speed of light in the vacuum. Yes, it should be the speed of light in vacuum. And I told you that the speed of light in air is quite similar to the speed of light in vacuum. So N air should be 1. And for N, for example, this case is water. So N water is like the still C over V water. Yeah. So we know that the speed of light in vacuum should be the fastest speed. And for all other material, the speed of light will only be less than or equal to the speed of light. For example, for the air, it is the same. But for the other material like water, glass, or even diamond, the speed of light will be smaller. Yeah. and in that case, the index of refraction will be larger. And yeah, so you can see here, this equation is like n1 times sine of theta 1 equals n2 times sine of theta 2, which means that if n1 is larger, theta 1 is smaller. If n2 is smaller, and theta 2 is larger, because it's still like on this side it only relates to the material 2, and for this side it only relates to material 1. And as I told you that the n for the air is smaller than the n for the water. In that case, the angle here should be larger. For the theta for the water, and it satisfies this equation. So yeah, so probably in high school you have calculate this one, give you the incident angle, and then with different material you try to calculate the refraction angle, something like that. Just plug in here and then press the calculator, then you can get the refraction angle. Yeah, so there is another phenomenon called the chromatic dispersion. In Chinese, it is called 色散. Which means the 颜色散开的意思. Okay, so chromatic dispersion of white light. So so you know when you have a incident wave going through the diamond or the glass or something like different case, then you see if the incident wave is white light, then you will see the rainbow for the refracted light. And the reason is that for blue component, which means that the wavelength is shorter, or the frequency is higher, is bent more than the red component. The red component means, you can also refer to red, orange, yellow, green, blue, and purple, something like that. Yeah, so it generally means longer wavelength, or lower frequency, or longer wavelength for the red component. The blue component means shorter wavelength or higher frequency. So passing from the air to glass, the blue component ends up with the smaller angle of refraction. So it's like for normal one, the blue light will bend more. So it is like if there is no glass here, then the light should go in this way. And for the red color, it bends less because this angle is smaller. And for the blue light, this angle is larger. So it tells you that the blue component is bent more. And from this side, if there is no two material here, then the line should go in this way. And you can still see the red line bends less, and the blue component bends more. So that's why we use the red line for the traffic light to represent stop, because sometimes there will be fog, and the fog is actually some water in the gas status. So we hope the red light can go through more. So we feel like we have the red light, and we hopefully there may be fog in between, which means there are some water between. And as much as the refracting angle is smaller, so we feel like the red light can go through it for longer distance. Otherwise, if the angle is larger, just like if we have a blue color here, and the refraction angle is larger, so it feels like it is easier to go to this side or that side, something like that. You bend for larger angle, which is not good because we hope everyone can see the red light, so that it can tell you that you must stop, something like that. Yeah, so passing from a gas area to end up with a greater angle of refraction. Each dot line represents the direction in which the light which would continue to travel if it were not bent by the refraction. Yeah. So here it also mentioned a phenomenon called the total internal refraction. In Chinese, it is called 全反射, total internal refraction, which means that it already tells you that when the light coming from like the material with a larger index to the smaller index, then the refracting angle will become larger. So that if this angle become larger and larger, then this angle may close to 90 degrees or even larger than 90 degrees. For that case, there will be no solution for the Snell's law, because you can simply imagine if just say N2 is larger, so it will for N1, suppose N1 is larger and theta 1 represent the so now we consider N1 is larger than N2, and now we can solve theta 2 by sine of theta 2 equals N1 over N2 times sine of theta 1. And now we know N1 is larger than N2, which means that N1 over N2 is larger than 1, which means that if sine of theta 1 is large enough, this one will be larger than 1. This one is large enough. Of course, if theta is very small, then even N1 is larger than N2, then this one is smaller than 1, and then you can find the angle of theta 2. But as you know, if theta 1 is large enough, which means that this term can be larger than 1, and we cannot find the real solution for the theta 2. Of course, in the complex domain, you can still solve it, but yeah, actually it's not the scope here. Yeah, so that's the case for the total internal reflection. So for the angle, if it makes this one equals to 1, and then you try to solve this term, then you will see the angle for the total internal reflection occurred. So it is like if N1 is larger than N2, and then we also assume sine of theta 2 equals 1, which means that theta 2 is 90 degrees. So now we should have N1 sine of theta 1 equals N2 sine of theta 2, which is N2, because we are already assumed that sine of theta 2 is 1. In that case, theta 1 is nothing but arc sine N2 over N1. So this is the angle when the total internal refraction occurred. And this one, we call it the critical angle. The critical angle. We may call it theta C here. Theta C here. Okay. Yeah, probably you should have learned it in high school. And yeah, probably for this one, you probably have not heard it in high school. And this is called the frustrated total internal refraction. 这是一个沮丧的全反射，沮丧的全反射。So now, yeah, I just tell you, but yeah, without too much calculation regarding to it, but yeah, it's just an interesting phenomenon. Actually, it's related to quantum mechanics, but yeah, still we will not cover that part in this semester. But still, I'll talk about it because here assume we have a 45-degree, 90-degree stream. So this is one of the 45-degree, 90-degree, which means that this angle and this angle are 45 degrees. This is 90 degrees to form a triangle. And this is another 45 degree, 45 degree. So these two 45 degree add up to 90 degree. If these two streams are touching each other, so actually this is like maybe we can just assume it to be a glass or any material, or maybe diamond. And here we have air. If these two streams are touching each other, then we can already assume there will be no refraction for this surface because they already touch each other. In that case, as much as the incident angle is 0 degree, so the light will go through these two stream system. And here we assume that the critical angle is smaller than 45 degree, or smaller than 45 degree. And here we leave a large gap between these two streams. In that case, the light will be total internal reflected, which means that all the light will incident from here and then go downward finally. But for the frustrated total internal refraction, it means if we just leave a very tiny gap between these two streams, then in that case, some of the light may be able to go through this gap, even though this light is larger than the critical angle. So part of it should follow the total internal refraction going this way. But still, there are some of the components can go through this gap, and then going this way. So it's just like no refraction here, but only part of it will go this way, but part of it will go in another way. So this is called the frustrated total internal refraction. Yeah, maybe we just stop here.